Hello, everybody. Good morning. My name is Saad Lahrichi. I'm a first-year PhD student at the University of Montana, working with Professors Jordan Maloff and Jesse Johnson. And today, I want to share with you all our project on predicting wildfire rate of spread using machine learning and remote sensing. And so, as we all know, wildfires are a global cause of concern that has severe human, economical, and environmental impacts. In 2017, the NIST reported that wildfires cost between $71 and $347 billion each year. And due to climate change, many regions are getting hotter and drier, which lengthens those wildfire seasons and exacerbates their effect. Now, fire management, mitigation, and prevention all hinge on our ability to predict the spread of fires accurately. Because in the case of a wildfire, there are actual firefighters deployed either at or a very close distance away from the very burning edge of those fires. And therefore, predicting that fire spread is essential to ensure not only the safety, but also the effectiveness of these interventions. Now, better wildfire mitigation also allows us to better mitigate climate change impacts, and that happens through reducing greenhouse gas emissions, which we've talked about at length during this symposium, preserving our carbon-storing forests, avoiding power outages, enhancing the grid reliability, and preventing transportation system failures. All of these help to break that reinforcing feedback loop of climate change on wildfires. Now, one of the quantities that are used to describe fire behavior is the rate of spread, or ROS for short. And it is defined as the speed with which the fire is moving away from the site of origin. On the right, you can see two superimposed fire perimeters with white arrows showing the evolution of the fire between the two consecutive timestamps. And so a major challenge of fire mitigation is the unpredictable behavior of wildfires. What we see here are growing perimeters from the 2018 Oregon wildfires. On the left is a plot of the state of Oregon, and the fire growing on the bottom left of that plot. And on the right, we've zoomed in on those perimeters. I want you to notice with me the erratic and unpredictable growth of the fire from one timestamp to the next, which lessens the effectiveness of those traditional interventions. Now, field managers have traditionally been relying on FLAM map and other statistics-based models for decision-making in firefighting. These models take as input the various factors that are known to influence fire spread, then they assume a functional form based on physical theory and lab observations under ideal conditions. For example, FLAM map assumes that all environmental conditions, such as wind and fuel moisture, are held constant across time. However, this assumption is, of course, incompatible with conditions observed in the real world, which significantly hinders these models' predictions and accuracy. On the other hand, advances in remote sensing, which again has been a very important topic this week or this weekend, have unlocked unprecedented access to data on fire behavior, which is leading to the potential adoption of generalized and more complex function finders like neural networks. And these neural networks are better suited to explain the observed behaviors and possibly even discover relationships we did not previously understand. Now, to realize how neural network works, we can, at a high level, obviously, we can look at the following example. What we see here are, on the left, you have our set of inputs. In this case, high wind, a steep topography, and dense fuel. These data are passed through each layer of neurons. And finally, the model produces an output, in this case, rate of spread of 0 chains per hour. When we compare this output to the ground truth, we realize it's a bad answer. Given these conditions, one would expect a much higher rate of spread. So what happens is that this feedback is used to update the model weights to improve its future predictions. At the next iteration, the new weights this time lead to a more realistic prediction, in this case of 46 chains per hour. Now, the challenge with neural networks is that they work primarily with data and don't inherently grasp physical concepts. However, we can leverage our current physical model to jumpstart their understanding of these physical phenomena that do impact those predictions. And this approach is known as physics-informed neural networks, which was mentioned this morning by Elizabeth Freely and termed as an ambitious approach used in remote sensing. These physics-informed models allow, or physics-informed neural networks allow these models to make more accurate predictions while respecting the established physical constraints. This results in improved prediction accuracy and reduces the need for large amounts of training data. And so this is what we have done so far. On the right, you can see two fire perimeters over a 12-hour period. The gray shows the previous perimeter, and the color contour depicts the current one. The darker colors signify short travel, while the lighter ones or brighter ones indicate longer distances. And so we have used the fire perimeters we got from NASA's VIRS dataset to calculate the distance that these recorded fires travel through each 12-hour period, which gives us the ground truth rate of spread we're trying to predict in this problem. We have then downloaded landfire.gov, NASA, and USGS data to get the input features that we need to train our neural network, and we match those values based on the specific fire event. Our next step would then be to train our neural network to predict the rate of spread given those natural conditions. This, of course, is a lengthy process that takes a lot of time because, as we've seen, those physics-informed neural networks take time with remote sensing, and so it's an ambitious process, but one that we're getting started on and that we're very excited about. That was almost all the time I had today. Thank you so much for your attention, and I hope this piqued your interest. If you have any questions or feedback, please feel free to get in touch with me, Jesse, or Jordan. And again, thank you all.